Good day, grade 12 chemistry students. Today, what we're doing is we're continuing to learn about rates. Particularly, we're going to take this learning goal that we have here and we're going to boil it down to something very elementary. We're going to learn about something called rate law. Okay, it's an equation. We're going to learn about it. I'm going to show you how to use it and what type of questions you'd have to answer in the future. Here we go. Rate law. Okay, so in order to understand rate law, we have to understand something called order of reaction. So basically, what the rate law is a mathematical relationship. It's a mathematical equation that is affected by various factors. Okay, so experimental evidence suggests that the rate of reaction is exponentially proportional to the product of the initial concentration of reactants. So product means multiplication when you multiply the concentration of reactants together. But here's a question for you. Why isn't the rate of reaction proportional to the concentration of products? Why do we only care about the reactants? That's a good question. Why do we only care about the reactants? Why not just uh, the products? Why the products have no impact on it? Well, let's think about it for a moment. So the answer to that question is that rates of reactions are determined by the number of collisions that occur between reactants. It has nothing to do with the amount of products because products don't produce like once you get products, the reaction is already complete. The reaction goes ahead once you have reactants colliding with each other, and that causes the reaction to occur. Now, this rate law that we're going to find, what it allows us to do is to find the rate of any given equation. As long as we know this rate law equation, you can find the rate of it as long as we know the concentration of reactants. So let me say that one more time. We can find the rate of any given equation as long as we know the concentration of reactants. Okay, so we're going to start talking about the rate law a little bit more specifically here. And when we write this rate law, what we really need to know is a balanced chemical equation. That's the first thing. And AX plus BY equals products. Now, we don't care about the products because they don't impact the rate of reaction. Now, A and B are going to represent the coefficients, and X and Y are going to represent the reactant chemical formula. Okay. So, for example, in the 2H2 plus O2 equals 2H2O, we don't care about the Y. And our reactants, in this case, X would be H2 and Y would be O2. The coefficients that we would have is 2 and 1. So this is the general form of the rate law right here. And what it states is that it will always be proportional. The rate R will always be proportional to the product of the initial concentrations of reactants. So we take the concentration of reactants X, okay, so take the concentration of reactants Y, and we multiply them together. And we have some form of exponent that it's raised to, okay? So our rate is measured in, again, moles per liter per second, or you could also write this as moles over seconds. The K is a constant, and it has different units depending on what type of reaction it is. X is obviously the concentration, so this is going to be my exponent for given reactant. So if we're talking about the reactant X, it will have a specific exponent, and Y will have a specific exponent, and these exponents are only going to be whole numbers, okay? Which I guess is pretty intuitive because math, you can't have really a decimal there. So in our class, we're only going to really deal with, you're only have a 0, 1, and 2, okay? Furthermore, if we look at it, K is actually at a specific temperature. So if you change the temperature, you're going to change the K value. And that means, so if we're going to find the rate of any given reaction, if we know the concentrations, it has to be done at a specific temperature. If you change the temperature, our equation is no longer valid because the K changes, okay? So this M and N are exponents that describe the relationship between, for M, it describes the relationship that X has on the rate. And the exponent N describes the rate with respect to Y. Okay, so how does N impact or sorry, how does y impact the rate? I'll show you what I mean. It's best to show you through an example so you clearly understand. So we call this exponent that we're looking at, m and n, we call them reaction orders, okay? And the reaction order is an exponent value that describes the initial concentration dependence on a particular reactant. So what impact does that uh, reactant have on the rate? So the overall order is pretty much we add up the exponents, and that gives us something called the overall order. So let's look at a specific example here. So here we have problem number 1. And it says the determined rate law for the equation for the reaction between nitrogen dioxide and fluorine gas. So these are two reactants, and so therefore they are going to end up going in here. And you can see the exponents for NO2 is 1, and you can see the exponent for F2 is 1. Now, that means the order of reaction with respect to NO2 is, we call NO2 a first order reactant because it has an exponent of 1. So therefore, if it had an exponent of 2, we'd call it a second order reactant. And F2, since it has a 1 there as well, it is a first order reactant as well. The overall order, define the overall order, and it doesn't really help us too much when we're talking about a reaction. The individual orders, 1 and 2, really help us a lot, but the overall order doesn't help us all that much. But the way we find it is you just add the exponents together, 2. Okay, so in this case, the coefficients really don't impact this at all. They will come into play later on, but it has no sort of bearing on this at all. It's just the exponent that determines what order it is. Okay, so we are still exploring this rate order thing. And if we take a look at this, let's say we have this equation, 2x plus 2y plus 3z equals products. Now, y represents chemicals, okay? Any chemical, it doesn't really matter. So therefore, we're going to have x, y, and z. And so right now, I've just made up these orders of reaction for it. It says 1, 2, 0. So x is a first order reactant, y is a second order reactant, and z is a zero order reactant. Let's explore what that means. What would happen if I doubled the concentration? Well, if you double x, we know that, so if you put a 2 here, that really represents that it's doubling it. 2 to the 1 is equal to 2. So if you double the concentration here, it will be 2 to 1. You're going to double the rate. This whole, whatever else is left here is going to be multiplied by 2. If I triple it, that means the reaction is going to be multiplied by 3. Okay? So basically, this is a first order reactant. So if you double something, it's doubled. And similarly, if I quadruple this, it will be 4 to the 1. I'm quadrupling my rate. Let's take a look at it there. Our second reactant, y. So if we double y, okay, so that means that it's going to be 2 to the 2, because now we have an exponent of 2 next to y. And that's going to be 4. So that means if you put a 2 in here, it will be 2 squared, that's 4. So if I double the concentration of y, that means my rate is multiplied by 4. If I triple it, it will be multiplied by 9. Now let's take a look at the last one where we have z is equal to 0. So anything to the exponent of 0 is, you should know, is, what is it, guys? It's 1. That's right. So if you triple it, it's still going to be 1. So this guy here, you know what? It doesn't matter what concentration Z is, because it's just going to multiply the rate by 1. So we don't even have to show this in our rate law because it has no impact. You can change your concentration of Z all you want. That exponent of 0 is going to make it 1 times. In other words, it will just multiply the rate by 1. It will have 0 impact. Okay, let's finally discuss how we're going to find this rate law. To find the rate law, you have to find K, you have to find M, and you have to find N. So what it says down below here, before we can find K, we have to find M and N. And the way we find M and N is we do it from experimental data. So the question will always give you some data to find M and N. Okay? So you have to look at a data table to find it. The questions will always have it in it. So let's actually do that. Now we'll go through one question. So the questions that you'd have to answer would look like this. It gives you a data table. It gives you a balanced chemical equation. And then it says, find the rate law. So to find the rate law constant K, we have to go through the following steps. We're going to find M and N first. But before we even do that, we write our partial rate law. So we say the rate is equal to K, which we don't know, and then we just substitute in our concentration of the name of our reactants in there. We have M and N. Now what we're going to do is we're going to try and find M and N. To do that, you have to look at your data. So you have 6 experiments to choose from. Using these experiments, you must determine the values of M and N first and then find K. Okay, so there are only 2 reactants, so you choose one to start with. We'll start with NO. So I have this slide here. You can pause it and write it down, and I'm just going to explain it to you as I go through it. So just pause it, record it if you'd like, and then I'll explain it to you. So let's look at experiment 1 and 2. And when we look at it, you'll notice something. You have 2 different experiments, okay, guys? And they have 2 different rates. That's the most important thing we have to understand, 0.02 to 0.08. So second experiment is going faster than the first. Let's look at the concentration of our reactants. Well, it's very important to notice that H2 is constant. Because H2 is constant, the only impact on our rate is the change in concentration of NO, right? So what's the difference between experiment 1 and 2? Well, the only difference is that we have doubled the concentration of NO. When we go from 1 to 2, we have multiplied the concentration of NO times 2. Okay? And what has happened to our rate? When we go from 0.0 to, or 0.002 to 0.008, you just divide the 2. So 0.0002 divided by 0.001 is 2 times. Well, we do the same way. 0.008 divided by 0.002 is 4 times. So therefore, the rate has doubled, or sorry, quadrupled when the concentration of NO has doubled and H2 is constant. So I've created this little chart over here, and I'd like you to do this for these questions. And it says at constant H2 concentration. So in experiment 1 and 2, so experiment 1 and 2, we have constant H2 concentration. NO concentration has doubled 2 times. The rate has quadrupled. So therefore, can anybody tell me what exponent should go here? What exponent would go when we double the concentration? Well, the answer is M is equal to 2. So we just found the concentration of M. Or sorry, we found the order of the reactant M. It's equal to 2 by doing this experiment. If you want to take a look at another couple of experiments here, let's just do it quickly, and we'll do the same sort of thing. If you wanted to do experiment 1 and 3, you can take a look at that. The concentration of H2 is constant from here to here. It's 0.04. Well, the concentration of NO is tripled. And if you take a look at the rate as well, when you go from 0.02 to 0.018, you divide those two numbers, you'll find out it's 9 times. So what's the exponent still that goes next to 3? The answer is 2. So we know for sure that M is equal to 2. Let's try and find N using the same data. Okay, so now what we want to do is we want to find N right here. Now to find N, what we have to do is we have to find 2 experiments where NO is constant. Okay, so I picked experiment 4 and 5. And if you take a look at experiment 4 and 5, NO is constant because it doesn't change. So I didn't change the concentration of NO. It remains constant. But I have doubled the concentration of H2. Okay? Now what happens to my rate? Well, it's also doubled as well. And because it's doubled, that means that my rate is doubled there. What exponent would go in for H2? Well, the answer is N equals 1. Now, if you wanted to try this again, we could try experiment 4 and 6 now. So if we want to do 4 and 6, just to double check our work here. You don't have to double check it, guys, but if you weren't certain, my concentration triples, and if you take a look here again, my rate triples. So therefore, you always like to put arrowheads on these so you're following which direction you're going, and that would be 3 and 3, so therefore the exponent would still be 1. Okay, so that's how you find the orders of reactants. What's the overall order of reactant if this now is equal to 1? Well, all you have to do to find the overall order of reaction is just add them together. It equals 3. I'm just going to show you this in case you want to copy this down. This is summarizing some of the things I just said, and hopefully it makes sense to you. So I'll just quickly go through these slides to save time, and you can copy down and pause them if you'd like. So this part here is saying that, showing you how to find n. Okay, so you go through experimental data to find n, and it's showing you that n was equal to 1, just like I told you in the previous slide. So you can copy that down if you like, just pause it and see it. So like I said previously, what's the overall order of reaction? What you have to do is just add the individual orders together, 2 plus 1. So the overall order is it's a third order reaction, okay? 2 plus 1 equals 3. So we haven't solved this yet. In order to find this equation, to find any rate, what you need is you need K, you need the concentration of NO, you need this exponent, which we have, in H2. So to find the rate, we have to have everything on the right side of this equal sign. Right now, we don't have K. To find K, what we're going to do is we're going to just substitute information where these red check marks are. Do we have information on the H2 and NO and the rate? Well, yeah, we do. We have lots of information on it. Recall what we just did here. We have 6 experiments which give you information on NO concentration, H2, and rate. So if you substitute any one of these equations into this rate law, you'll have NO, you'll have H2, and you'll have rate, and we know our orders. We can solve for K. And once we know K, it doesn't matter what we substitute in, we're going to find K, and we've solved our problem for K. So let's find K right now. I'm going to use experiment 1 data. So just this data right here, and substitute it into my equation. Okay. So what we're going to do is we're going to sub in experiment 1. Okay. It doesn't matter what you want to do. If you want to do a different one to check to see if it works, it does. So we're going to just throw in our rate here and substitute all our values in for R, NO, and H2. Okay, so we've substituted our information into our equation. Now I'm going to square this first and then multiply it by this and watch my units, okay? Notice how I have big M here? Well, that is this here. It's just moles per liter, and it's just big M, okay? So let's do this side right here, and let's see what that equals when we do our math. Okay, so we're just following through with our math here. This is the first step. I just squared that. I'm going to multiply these two together. So that's our answer there. Notice how we add our exponents. This is like x squared times x is x cubed. M squared times m is m cubed. And then what we're going to do is we're just going to finish off our algebra, and we're going to solve for k here. Okay, so I've actually found my k value. It's right here. Take a look, take a look at my units there. They're kind of messed up, 1 over seconds per meter squared. Let me show you where we get that from. Look at the units here. We have meters per second divided by meter cubed. Remember, math leads, guys. If you have meters per second, what you got to do is you got to flip the second one and multiply by its reciprocal, okay? So that has an exponent of 1, so that has an exponent of 2. The answer will be seconds per meter, per mole per liter squared. The big M means moles per liter. Remember that. That's it. The final step that we have to do is we have to just write our rate law out. And all we're going to do is I'm going to substitute my K back into my equation right here. And this is what it looks like. So this is my rate law, the final thing that we have here. And if you take a look, I've just substituted in for K. We found M and we found N earlier. This is 1. Okay. So that's my rate law. If we have the concentration of NO and if we have the concentration of H2, we can find the rate at a specific temperature, okay? So at a specific temp, you can find the rate of any given reaction. We found M and N through experimental data. We found K by substituting one of our experimental datas in there, and that's our rate law. That's about a 6 or 7 mark question. That's at the end of this. Sorry, this video is so long, but that's the end of the lesson, and hope to see you guys soon. Enjoy your night.